a non-parking area. They said maybe master student. This is in France. I think it's just gonna be. I think so. I'm hoping it's you know where he went? Guatemala? I mean, I knew. I thought Colombia, but I don't know.
Who went somewhere?
Dr. Wood.
Oh, wow. I hadn't heard that. Cool. Did you see where Dr. Dixon went? Oh, I went to Maui. Posted all these pictures on Facebook with her son doing all the cool stuff. Yeah. They did something where they climbed up a waterfall. They zip lined down back into the water. It was like, whoa. Yeah. Yeah. Her son's a senior in high school. Yeah. What? All right, so this is where we ended. Do y'all remember anything about it? Not a darn thing, huh? Okay. Okay, so remember that MO is molecular orbital theory, okay? And you take the p orbitals, what we're going to do, and you put them together in all the possibilities, basically, okay? There were 2 p orbitals in ethylene, okay? Remember, ethylene has 2 carbons, double bond, okay? So they can go together so they're in phase or out of phase. Those are the 2 possibilities. In phase is when you create a bonding interaction. So here we are bonding. That's lower in energy than when they're opposite, okay? That's called anti-bonding. It's probably totally new terms that you have never used before, okay? And I think if you do some inorganic, you'll talk about this a little bit in there, probably in a whole different vein. There's a whole bunch of this. When you fill the molecular orbitals, you fill them from the bottom up, just like you do with atomic orbitals, and you put 1 electron in, and then you have 1 go in the opposite directions, just like you do atomic orbitals. The filling is the same, but there's only 2 electrons, 1 from each p orbital. So we're not worrying about all the rest of them. We're only focusing in on the pi electrons, okay? Highest occupied molecular orbital. That means which orbital is highest in energy and has a length, okay? Lowest unoccupied molecular orbital is which orbital is lower in energy and has no electrons in it. It's unoccupied with a length. Okay, so that's what that stands for. Now, here, there was only 2. So that was kind of, but we're going to move on. Oh my gosh, it's okay. We're going to do it super systematically, and that will make it, that will make you able to get it. Okay, we're going to go very systematically through the steps of how to do it and how to do it. Okay, so what'd you do for spring break? Let's see. I think, I don't know if I needed that or not. Maybe not. Maybe not. Maybe I'm good. Okay, I got 16. Is that it? 1, 2, 3. 16, yeah. Okay, let's see what y'all did. We got like all of them. Nobody went fishing. I had someone go fishing in Robert. Fishing or hunting? Isn't it hunting season? We're talking all about the does on the news.
I mean,
what?
you can hit them with your car, but you can't.
Oh, okay. Well, I thought there was a period of time where there's like does.
Yeah, November.
Oh, it is? See, I have like no idea. Okay. I grew up in Chicago.
Do they not have any deer there?
Yeah. Well, if you drive out of the city, you might see a deer, and then, but yeah, not really. I saw more deer moving here. Okay. We're going to go to the next slide. Okay, so items of note. Okay. The green and blue colors just distinguish the sign of the wave function. It's just the opposite, okay? Like I said, we used to do them where we would have this and people would go plus and minus, and then people started thinking the electron was in the minus, and because that they don't want you to think that way, so we stopped doing that. But you may run into a book or something that still uses that. The number of p orbitals you put in, that's how many molecular orbitals you get out. So you notice in the ethylene example, we put in 2 p orbitals. How many molecular orbitals did we get? 2. Okay? You will have the same number of bonding and antibonding molecules for what we're doing. Okay? So the bonding, so we got 2, okay? And it's always, we're always going to do an even number. We're not going to do periodical stuff. We're just going to do an even number. So if you put in 2, you get 1 bonding and 1 antibody. If you put in 4 p orbitals, how many molecular orbitals are you going to get? 4. And you're going to get how many bonding? 2. And how many antibodies? 2. Okay? Like I said, we're going to be real systematic about it. Okay, the asterisk signifies anti-bonding molecular orbitals. That's the pi star stuff. If your molecular orbital that you drew has more nodes than bonding interactions, then it is an anti-bonding molecular orbital. They're not necessarily going to be all nodes. You can have some bonding and anti-bonding in the same picture. Okay, you'll see as we move on and do a couple more. Okay, there are some symmetry rules. I'll kind of show you that as we go. And you fill with electrons from the bottom to the top. Bottom is going to be lowest energy, top is going to be highest energy. We're just going to draw it that way. Okay, so we're going to start at the bottom of the slide, basically. Okay, remember that you get 1 electron from each p orbital. Okay, so those are kind of the basic rules. I don't know if rules is the right word, but that's kind of how we're going to do it. So we're going to do 1,3-butadiene. Okay, so notice that we have a p orbital on each one of these carbons, right? Because every one of them is sp2 hybridized. Okay, we're going to put in 4 p orbitals, so we're going to get 4 molecular orbitals. 2 will be bonding and 2 will be anti-bonding. And now we're going to draw the pictures. Okay, are you with me so far? Okay, just think systematically. It's a whole nother way of thinking about molecules and their electrons, which kind of is amazing, really. Okay, so I'm starting at lowest energy, so I'm going to draw a line. That's my sigma bonds between the carbons, basically. And I had 4 carbons, 1, 2, 3, 4. Okay, so those are my 4 p orbitals. Okay, now lowest in energy is going to be where every one of them is colored the same. They are in the same phase. So that would mean that this, and this would all be purple, and the bottom ones are all white. So between all of these, we have bonding interactions. Remember that because p orbitals have a top and a bottom, you get your whole, even though it looks like 2, it's 1. I guess I don't know how else to say that. Even though it looks like 2, it's 1. Okay, so notice that we have how many bonding interactions in there, would you say? There's 1 between these 2, 1 between these 2, and 1 between that one. So there's 3 bonding interactions. I'll write int. Okay, does that make, we're getting it now? Okay, now, how many nodes was in this one? I know you know that. 0. There's no nodes in that, right? Nodes are when we have them flipped. Okay, so what do you think is going to be the highest energy one? The one where they're all flipped, okay? How many nodes will that one have? Let's look at it. Since those are the two extremes we did in the other one. Okay, so I'm going to go up, down, up, down. My little cross kind of got skewed there. Notice where the nodes are. Okay, there's no bonding interactions in that. Those are the two extremes. So how are we going to get the ones in the middle? Well, we have how many nodes up here? 3. How many we got down here? 0. So guess what we're going to go? 0, 1 node, 2 node, 3 nodes. Okay, so I'm going to start by drawing my 4 p orbitals on their little line. And then we'll figure out how to color them. Okay, the fourth one, I don't know. Okay, so how do you think you could get this to work out so that you have 1 node? What do you think? Possibilities. Okay, so you would go. So basically, it'd be up, up, down, down. So between here is a bonding interaction. Here's my node, and here's my next bond interaction. See that? So we have 2 bonding interactions in 1 node. Okay? You with me? Okay. All right, notice what we didn't do. So I'm going to write over here what we didn't do. We didn't do this. We didn't go up, down, down, down. That has only 1 node. What's wrong with that? Do you see how much more symmetrical this is? You want to aim for symmetry. That's kind of the symmetry rules. Okay, that's why that one isn't correct. Okay, so we're just going to put an X through it. Okay, it has only 1 node, and it still has 2 bonding interactions, but it is not correct because it isn't symmetrical. Okay, all right, so go look at the next one. Okay, so we have 1 node and 2 bonding interactions. So how can we do this next one? We want to have 2 nodes, and we want to have how many bonding interactions, you think? We had 3, we had 2, we're going to have 1, and up here, how many bonding do we have? 0. Okay, so notice that bondings is going down as we go up, and the number of nodes is going up. 0, 1, 2, 3. We're going 3, 2, 1, 0. So how do you think we can do this? Remember to try to keep it symmetrical. Okay, so what should we do? Okay, that gives us a bonding interaction. And then what do we got to do with the ones on the outside? Opposite. So this one will be down and this one will be down. And I bet you can color that in a whole lot nicer on your little papers. Okay, so notice we have 2 nodes and 1 bonding interaction. Okay. I wonder if I could select this and move it. What do you think? Ooh, looky there. All right, I'm going to try that because I want some space. Okay, because now we're going to name them and do all the stuff. Okay, so let's get black. All right, so here are my deals. Those are my little levels. Okay, bottom, more stable, lowest in energy. Top, high energy, less stable. Okay, just like you do the atomic orbitals. Okay, now name them. Okay, so the bottom one is going to be pi 1. You could use the size 2, but I like the pi's better because I like the stars. This is going to be pi sub 2. Okay, now what are the next two going to be? Well, they're going to be 3 and 4, but they're going to have something else. They're going to be pi 3 star and pi 4 star. The star means anti-bonding. Okay, so these are anti-bonding molecular orbitals. And these are bonding. Okay, now how many electrons am I going to put in these MOs? 1, 2, 3, 4, 5, 6, 7. How many do I have? I have 1 from each p orbital. So what does that give us? 4, right? Okay, so how do I put them in here? You start at the bottom and you fill it up. There's 2, and then we do the next one. Okay, that's it. So which orbital up here is the highest occupied molecule? Now we got some choices. So which one is the highest occupied molecule? Which one? Which is highest in energy and has electrons in it? Pi 2. This is it. Highest occupied molecular orbital. Has been referred to as a HOMO for many years. Okay, what is the LUMO, the lowest unoccupied molecular orbital? Unoccupied. There isn't a LOMO. They didn't do that. Lowest unoccupied molecular orbital. Okay, is pi 3 star. That's the LUMO. Okay, I'm going to put a line there just to keep it sorted. Okay, now why is that even important? Okay, so let's say that we zap this with ultraviolet light. Okay, 1 electron is going to go from the pi 2 and jump up to the pi 3 star. Okay, and that difference in energy is going to vary as you have more and more conjugation and you have more and more p orbitals all lined up by each other. That energy difference gets less and less and less. The more highly conjugated a molecule is, the more you're going to get color. And that's part of why you get color. Is because it's easier for an electron to go up. Okay? So it will jump up and then come back down, and you can actually measure that difference in energy. Okay? Using a UV vis. We're not going to do that, but you might do that in a minute. Okay? All right. Also, well, we'll get to that other thing. All right, so here is my pictures, drawn really nice. Do you have those? I didn't give you the pretty pictures? All right, well, you'll get them when you get the next thing. Okay, here they are drawn really pretty with the nodes. Here's your nodes in here. Okay, with the blue and the green. This is your bonding. This is your anti-bonding. Okay, and then here are your, let's see if I can get that. Okay, and this shows the psi designation. Wow, I love when I do that. You have to kind of lock it, and sometimes I don't know. Okay, this is the psi designations that you'll see, but you see they don't put the stars. I really like the stars because they tell you that it's anti-bonding. Okay, pretty straightforward. Okay, now when drawing MOs, keep your bonding interactions to the middle. That's a really good tip to remember. Okay, that'll help you with the symmetry rules. There is a term symmetric or asymmetric. Asymmetric has to do with it's exactly the opposite. It's kind of asymmetric. Start with the most stable, put it on the bottom. Remember to count 0 nodes on up. Go 0, 1, 2, 3. Okay. All right. Let me see. I don't know what my next slide is. Oh, all right. We'll do that. I think I have to add a blank. Do you have another blank? No. Okay. I'll have to add a blank. Okay. We all got it. Yeah. Perfect. Okay. All right. So let's say you're going to do 1, 3, 5 hexatriene. Okay. So first of all, if I say draw all the molecular orbitals for 1, 3, 5 hexatriene, and then I go down the line and I tell you to label them, bonding, antibonding, give them their names, put the electrons in there, label the HOMO and the LUMO, all that stuff. Okay. So 1, 3, 5 hexatriene. So where should you start? What do you think would be a good way to start? Just draw the compound. Amen. Okay. 1, 2, 3, 4, 5, and there's your 6. Okay. So it really helps to draw it out so you can see what you do. Okay. How many p orbitals am I going to have in these pictures? 6. 1 from each carbon of the double bonds. Notice that it's conjugated. Okay, so I'm going to have 6. I don't know if I can do it now that I drew that up there. I'll try to write smaller. Okay, there's my straightish line. And I'm going to go 1, 2, 3, 4, 5, 6. Okay, I'm starting at lowest energy. You could start at the top. There's no reason not to, but you'd have to start at high energy then. Draw them in the order. Okay, so what's going to be lowest energy? All the bonding interaction, all the way across. Okay, so I'm trying to color them in. This thing doesn't color very well. 1, 2, 3, 4. Notice I got 5 bonding. Okay. Okay, how many molecular orbitals should I get out of this picture? If I'm putting in 6 p orbitals, I should get how many MOs? 1, is that it? What? 6, okay. How many will be bonding and how many will be antibonding? 3 and 3. Okay. All right, so you could do this and just put all your little lobes, 2, 3, 4, 5, 6. Do you think I'm going to fit? No, me neither. 1. I'm trying to get smaller. I remember doing this on the chalkboard one time, and I wrote on the wall to get the 6th one. Back when we did chalkboards, I used colored chalk and wrote on the wall. Okay, so can you tell me what you think will be the 2nd one up? How many nodes do we want to have in this one? I may have to write some up there. Huh? How many nodes should I have in this one? How many nodes do I have in this one? 0. So I should have, so what do you want me to do? How could I get 1? What? Yeah, put it in the middle. So I'm going to go up, 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 and then I'm going to go down, down, down. And y'all, it doesn't matter if you colored down, 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 and up, 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 right? Okay. All right, so here's your bonding interactions. And here is your node. Okay. So what do you think? How do you think we're going to do the next one? How can I get 2 nodes in the next one up? There's a better way to do it than on the ends. Bends isn't a bad idea, but there's a better. What? Go 2 by 2s. Go by 2s. So we got, look at that nice symmetrical thing. Okay, so we put it in, keep it as even as you can. That kind of helps to draw them right. All right, now that's 2. Now how are we going to get to 3? What do you think? Just look at your possibilities. We want 3 nodes. How many bonding interactions do we have in the one below? 3. Okay, so we're going to have how many bonding interactions? 2.
So up, down, down, up.
Okay. Up, down, down, up, up, down. So that gives me 2 bonding interactions and 1, 2, 3 nodes, and we kept the bonding interactions to the middle. Okay. Now I need how many more pictures? 2. All right, so we're going to go over here because that's life with a horizontal board. Oops. I try to keep my lines nice, but okay. So we're going to go to this picture here, the one on the bottom. Okay, now I need how many nodes in this one? 4. And how many bonding interactions? 1. Okay, so what do you want to do? Besides go to lunch. Wait, what do you think we should do? Okay, wait. Okay, I got up, down, up, up, down, up. Okay, so there's my 1 bonding interaction in the middle, and I've got my nodes. Okay, and then what's the last one? Alternate, right? Up, down, up, down. Up, down, up, down. So all we have are nodes. Worked out, didn't it? Okay, so I'm going to name, okay, so which ones are the bonding? The first 3, okay? So that designation is going to be pi 1, pi 2, and pi 3. Okay? The last 3 are anti-bonding, right? Okay, so this is going to be pi what? 4 star. It's a 4 star. Okay, this one is going to be pi, this is above pi 4 star. This is pi 5 star. Look at there. This one is a pi 6 star. You didn't even know there were hotels like that, did you? Okay. All right, now let's put our little electrons in there. How many electrons are we going to put in there? 6. Yeah. 1 from each of these p orbitals. Okay, so we start at the bottom, and how many we put there? Right, 1 up, 1 down. Next one we go, that's 1, 2, 3, 4, 5, 6.
Where do you get? How do you
What?
know that those ones are anti-bonding?
Because they have more nodes than bonding interactions. Notice that pi 4 star has 3 nodes and 2 bonding interactions. These have more bonding interactions and less nodes. And the bonding is always lower in energy than the anti. Okay. Okay, so which one are you going to label LUMO and which one are you going to label HOMO? And who's LUMO? Pi 4 star. Look at that. You little MO theory people. You're getting it. Just be very systematic and you'll be fine. So yeah, we can go to 4 pi star until you get to the test. No! Okay, but we're not gonna. Okay, now what about something like this? 1,4-pentadiene does not have conjugated orbitals, okay? So because it doesn't have that, it won't have delocalized electrons, okay? Basically, it's going to be 2 that are going to be just like us, okay? So you notice that we didn't stick methyl groups on there and all that because all we're looking at is electrons. Okay, if you stick those on there, it doesn't change your basic pictures at all. Okay. Okay, so these MOs have the same energy as those of ethylene. They're just there's no interaction in here because that's methylene in between them. Okay, I'll write not conjugated. Okie dokie. Okay, what about if they're right next to each other? Remember, those are called chemenes, chemulated dienes, okay? The thing about those is, what is the hybridization of the carbon in the middle of the system? What is the hybridization of that carbon? Do you remember? Yeah, it's sp. It's just sp, okay? And you have 1 p orbital going this way. Oh, that's what my picture is. You have 1 p orbital this way and 1 p orbital that way. And so because of that, these 2 p orbitals can't interact with each other, okay? You have to be conjugated in order for that interaction to occur, okay? There's no special stability. The pi systems cannot interact because they're not parallel. One's going this way, one's going this way. They're orthogonal to each other. Have you heard that word before? Did I spell that right? Is it O-N-A-L or A-N-O-L?
I think you're the only one.
That was supposed to be, I was going to put a question mark on it because I was wondering about the spelling here. I'll go. Nobody finds us online and yells at me. Okay. Now, the whole reason we did this was to get to this. Okay. The Diels-Alder. The highest occupied molecular orbital of 1, the HOMO of 1 molecule, is going to react with the LUMO of the other. Okay, so notice that when this is the diene system, this is the highest occupied molecular orbital. Do you see how many nodes are in that? How many nodes are in this? There's 1 right there. Okay, it's going to interact with the LUMO of other one. And so notice that where they're making the new sigma bonds, we match. Okay, that's kind of why we're doing it. Okay, you can also do it the other way. It doesn't have to be the HOMO of the diene. You could use the LUMO of the diene can react with the HOMO of the dienophile. but it's always the opposite, which is the weirdest thing to think about, isn't it? Am I blowing your brain yet? Or did I already do that a couple weeks ago? Because, but there's no electrons in the LUMO. Don't you think that's weird? I think it's weird. Yeah. I think an electron must go up there or something like that. It's weird. Okay. The Diels-Alder reaction is stereospecific. I might have told you that already. The stereochemistry of the starting material is retained in the product because there is syn addition to the alkene. The cis-trans relationship of the substituents in the alkenes and or the dienes are retained in the product. That's part of why they believe in this homo-lumo thing, okay? Because that explains why this is true. It explains something else too, but we haven't got there yet, okay? So here's our diene and our dienophile, right? Okay, 100-degree C benzene, kind of typical. Even though the one y'all did in class worked at room temperature, you didn't have to do that. All right, so what do you get? Do you have any idea? None? All right, wait, can't handle none. All right, so here's our diene. Okay, here's our dienophile. I'm going to write pH for the benzene instead of all that. And is this CO2H? Okay, notice that the benzene and the CO2H are what to each other? What are they to each other? What kind of double bond is that? Cis, right? Okay, so in the product, they should still be cis, okay? So when we do, okay, now can you draw the product? And if you have to do that to figure it out, that's quite all right. Okay. Notice that the CO2H and the benzene ring are on the same side. You still get cis to each other. Why didn't I just do what I want? Okay. This is the new pi bond that you got over here. Okay. That make more sense? Yes, no, maybe so. All right, how about this one? Oh. This is cyclopentadiene, that's your diene. This is your dienophile. Okay, what are the two ester groups to each other? Cis or trans. So what should they be in the product? Okay, can you draw it? Okay, remember that your diene, oops, I didn't draw it very well. Okay, you just have that extra CH2 up there. And we're going to go like this. CO2CH3. Go down here, CO2CH3. All right, so we're going like that. Remember, it doesn't matter if your arrows go clockwise or counterclockwise. It's all occurring at the same time. Just go one way or the other. Don't have some going clockwise and some going. Okay, so you think you got it? Okay, so here, get a color. Here is that 5-membered ring that you started with, is there. Okay, that's this. Okay, notice that the two esters are what to each other? strands. One's up and one's down. Doesn't matter which one you make up and which one you make down because this is symmetrical. Right? Okay, now the other way, I bet this picture is the other way of drawing it. Yeah. Have you seen those kind of pictures? Okay. When you look at this, remember that this bond is in front of this bond. Okay, which is why there's that little space there. There's not a carbon there. Okay, if you're going to draw it yourself on your piece of paper. Oh, I was explaining distillation. It happens. Okay, and you're going to draw this. I mean, I'm not going to expect you to leave a space there. Okay, I mean, I'll know. But a couple tips on drawing that, if you want to try to draw it that way, is make these two lines parallel. Okay. You're going to go up and down. Now, when you do the bottom one, don't line them up. Make them be offset. That gives you space to do this. Okay? Just some tips. Okay? And then this is just like, you know, the equatorial axial, just like we did before. Okay? That's what these are. Notice that this one's down and this one's up. And this bond is just being shown in front of that bond. That's why the space. If you draw them big enough and small enough, you don't even have to do that. Okay? Does that make sense, that picture? Okay. Because sometimes that floors people. All right. So this is, let's see if I can do it. I feel like it's off by like a whole. This is that dying, that's where it was. That's where it is in that picture. These are your new bonds that were formed. This bond and this bond. So if I give you this picture and I tell you to go backwards, would I do that? Probably. Okay. You have to figure out where to cut it. Yeah. Okay. Now, what if your things are unsymmetrical? Okay. So you'll notice that this compound has a D in it. That D does not mean deuterium. Okay? It means electron domain. So what do you think the double means? W means? It does not mean tungsten. No tungsten in this class. What? Electron withdrawing. Okay? Remember that that is a good thing to have on the dienophile, and electron donating groups are good to have on systems. Okay? So here is two compounds that have an electron donating group and an electron withdrawing. Notice that the electron donating group up here is an O. Okay? O is electronegative, but it has those lone pairs on there that can go in and do resonance. Okay, that's an electron donating. So if you drew your resonance form for this, notice where the negative ends up. It ends up on that carbon right there, which is this one right here. It has a purple dot by it now. Okay. This one, notice that we don't take the electrons from the O and try to push them in. You can't really do that because you don't have another double bond to move over. It doesn't work. It's going to be electron withdrawing. Carbonyls are electron withdrawing. So when you draw the resonance form for this, you're going to go out to the O, which makes that negative, and this carbon ends up positive. Remember, the reason that we draw resonance forms is to see reactivity, okay? Overall, so if we had, this would be your delta negative carbon, and this would be your delta positive carbon, okay? The positive and the negative always go together. The most negative goes to the most positive. Remember, all of this class is negative to negative to. Okay, so you have to find the highest electron density and the lowest electron density spot sometimes to know how to put it together. So it only makes these two sigma bonds. Those are the only ones that get made. Okay, this does not occur where it's flipped the other way. Okay, and in this example, they just flipped this one. Does everybody see that those are the two possibilities? You can put them together this way, or you can put them together that way. Okay, which one does it do? It only does one. Okay, and the way to figure it out is to look at the resonance forms and find the most negative part and the most positive part and stick those ends together. That's how you know that that's your product. Make a sort of sense? All right, let's try. I think I got one to do. I'm sure I am. Okay, so here is another one where they have the donating group down here. Okay, so notice that instead of off one of the carbons in the middle, notice that you can keep going on the resonance all the way to this carbon right here. Okay, so this is the delta negative spot, and this is still the delta positive spot. Okay, so you may have to draw them out and look at them and go, okay, where is my negative spot? Okay, so we're going to put the minus to the plus. Okay, and then here's what you get. Okay. And that'll be on your complete slides too. Okay. Okay. All right. Now we're going to practice, I bet. Okay. So here we have a diene and a dienophile. And, oh, I didn't have a practice. Hang on. I'm going to jump.
2 slides ahead. Yeah, no,
Go one more. There? Okay. Okay. So we'll look at this. Notice that this one, the methyl groups, are electron donating groups, okay? But they are not resonance. They're just stabilizing groups. Remember when we did primary, secondary, and tertiary carbo? Which one was the most stable? Tertiary, okay? So if you draw a resonance form for this, okay, notice that the plus will be here and the minus will be here. So this is still going to be your negative site. Okay, so let me write CH2 so that it has a lone pair and a minus. Okay, this is the CH3. See, I can't write over here. This is so irritating that it does this to me. Okay, how about the top one? Where is the positive part going to be? Which carbon of the double bond is going to be the positive part? The top carbon or the bottom carbon? Well, do the resonance. I'm going to go up with this resonance because I feel like I'm... See, it's up there. So this carbon is going to want to go to this carbon. Okay, so the easiest way to do that is to flip one of them. I don't know which one was flipped in that original thing, so I'm going to flip the first one and put it like this, okay, plus this, and now do your arrows. So figure when there are two unsymmetrical ones, figure out which one is the negative carbon, which is the positive, and kind of like blank. Okay. All right. So I don't know which one I flipped. Yeah, I should have had the order a little different. I flipped the top one, the right one. Okay. Now, this one, you still got, that was kind of exciting. You still got some of the minor product. Whereas on the other one, let's see if I can get it back. Is that back? Yeah, the arrows are lined up now. Okay. Why do you think you got some of the minor product? And before we didn't get any. Because this did not contribute resonance. Okay, that's how come resonance is such a strong stabilizing factor. Okay, so look at the bottom one by Wednesday and see if you can figure it out, and then I'll do those other 2 slides. Then I skipped those. All right, you got lab today? You don't know? Or this week, you got lab this week?